Okay, we have a quick adjustment here. This is actually machine learning session 6, but we're going to do the first half of the session 7 content, and then we are going to, which is neural networks. So we're going to talk about neural networks today. And then next time when we meet for regularly scheduled class, on Monday, we're going to cover the hour session of modeling methodology that we're missing here. And then we'll do the second half of this lecture content, which is large language models. So that's the plan. We also have office hours on Sunday. That's still occurring. That's 9 to 10 on Sunday, and we're going to extend those longer. So if you guys have homework questions, we can cover those on Sunday. We can go through the homework together, just like we normally do in class, and uh, and we'll extend that deadline for that homework as well to Sunday, since we're gonna talk about it then. Okay, so that is the plan for the adjustment with the snowy Midwest weather. So session 6, doing the first part of session 7 content here. Let's talk about neural networks. We've been building to this over the entire course, so I think this is pretty exciting. These are very, very powerful machine learning models, and they're typically referred to as actually deep learning. So you can now say that you have some background and experience in deep learning methods, particularly neural networks here. So we're going to start to introduce some terminology around neural networks that are a little different in terms of uh, how they refer to the things that we know and love about the formulas we've been working with through linear regression and logistic regression, that y equals mx plus b, betas. We've been calling them parameters. Now we're going to evolve our technology or our terminology one more time to use the same terminology that they use in neural networks. So remember, a really big goal of this class is to give you the capability to continue to learn about this information and to use the right keywords when you're searching things online to dive in and learn more. So this should enable you to really dive in from a terminology and overview of understanding perspective for neural networks. So what are neural networks? Neural networks are a subset of machine learning, and they're typically referred to as deep learning. And they're models inspired by this structure that we have in our human brain. In our human brain, we have, see my mouse, there we are. We have these neurons, these that are made up of a cell body and a nucleus, and they have these information pathways, these axons that connect them to these axon terminals and can send messages throughout our brain. So these neural networks sort of replicate that framework in a very oversimplified way. So they consist of these nodes, these central nodes that apply some mathematical computation, and then that ships this information to other nodes that then apply computations and process that information and send it out. So they are, when you hear people speak about neural networks and how they are like our brain, I think they are like our brain in that we're trying to leverage that structure, that framework of sending information, transforming it, and then sending it somewhere else. But in reality, our brain is probably much more complex in the interactions that are happening biologically here. This is neural networks are probably a very gross oversimplification. So they're not really like the human brain. I guess is the emphasis I want to put here. So neural networks consist of interconnected nodes known as neurons. So this is the first piece of terminology here. Nodes, neurons, these circles typically represented in pictorially are neurons. And they can learn and recognize patterns in data by adjusting the weights and the biases of these connections. So keywords here are weights and biases, and I think you guys are gonna Be excited to find that these are exactly the same things that we've been working with. Um, I want to look ahead in these. I have to look ahead in these slides real quick to see when. Okay, yep, we're doing. I have a spot for talking about that later. Okay, we'll continue here. So some terminology here. The 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 nodes or drawn here. The neurons or nodes are the basic units that process the input and generate outputs through activation functions. So each of these circular icons in our graph are meant to represent a node. And I'll talk about this later, but this is actually going to be equivalent to logistic regression, essentially. So this is basically a bunch of logistic regressions operating together. You can kind of think of it like that. We'll build on it with that knowledge. Neural networks are typically made up of layers. So we have a input layer where these are all the features that you're sending to your neural network. Maybe you're asking it to predict a binary classification problem where it can be the probability of output 1 and the probability of output 2, the probability of 0, the p of 0, and the p of 1. Perhaps we're asking it to uh, tell us if this email is spam or not. So what is the probability that it's spam? Maybe 0.7. What's the probability that it's not spam? Maybe 0.3. And what's the information that we pass to that neural network? Certainly it's the content of the email, but maybe we pass other things to it. Maybe we pass like a timestamp to it when this was received, who sent it to us, the sender. Maybe there's some textual information here. Or if this is a house, input features would be, the number of bedrooms and the square footage in the house. So these are input features just the same as input features have been for the rest of machine learning. And then we're trying to predict output. So this input layer takes in the raw data, the raw features, the raw information, and then feeds it through the neural network. So in this first node here, this will take in the information, a timestamp information, apply some transformation to it, and then send this information to these nodes downstream. The hidden layers, these perform computations by applying weights and biases and activation function. And then our output layer produces the final prediction of input. So we have an input layer, we have 3 hidden layers here, and we have an output layer. In this network, this is a fully connected network. There are different architectures for neural networks in terms of, how, in this case, each node is sending information to every other forward layer in the network. There are different types of architectures and representations of networks that you can apply. This is a fully connected network. What's an example of a problem that we can solve with a neural network that we couldn't solve with our other methodologies that we've talked about, other algorithms we've talked about so far? The hello world of image problems, of image, I'm trying to think of the right word here, of, yeah, image recognition is this thing called the MNIST data set. So the MNIST data set contains over 70,000 images of handwritten digits. So they have all these handwritten digits. Somebody wrote 0 and somebody wrote 1, and it has kind of a fun story behind it. Back when they were back in the day, when they were trying to train a machine to read addresses handwritten on envelopes for automatic processing at the post office. This is how this data set was created. They wanted to be able to automatically read addresses off of letters that people handwrite so they could ship that, efficiently to the right area. So they could route letters automatically. And that's the foundation of this data set. Today, it's really used as a baseline data set. So when new architectures for neural networks come out, new methodology comes out, they'll say, hey, it performs X better on the MNIST data set. This is how it performed on the MNIST data set. So it's really sort of a thumb in the air and a way of like testing the quality of different approaches and implementations in a way that can be compared to each other. So there's a lot of images and they're fairly well curated. So the nice thing about this data set, it's a pretty clean data set. It's not very noisy. So they're pretty, I think you and I could look at all of these numbers and maybe a few of them are confusing. Like this one might be kind of confusing and there's a couple of them that are hard, but generally we as humans can get almost all of these correct. The way these are represented are in 28 by 28 size pixels. And it creates 784, so that we have 784 pixels in an image. We'll talk about this, I think, on the next slide, but these are our features. You might ask, what are the features for a data set like this? Well, our pixels actually end up being our features. So our training set, we have 60,000 in our training, 60,000 in our test. And these images are grayscale, so we don't have to worry about some of the complexities that come along with color. But the way that this number is actually represented as a numerical representation into the neural network is pixel intensity ranges from 0 to 255. So here where it's like the center of this O, it's going to be 255. It's going to be the darkest value. And then in these white spots, it's going to be 0. So each of these pixels we'll see in the next couple of slides range from 0 to 255. And then, so that's our X. Our X is, we have 700 and we have X sub 1, X sub 2, and we have X sub 784. So for each image, we have 784 features. 784 elements of input into our neural network. That means that input layer we have X sub 1, X sub 2, X sub 784. We have 784 input nodes into our neural network. And each of these nodes has a value, 0. When we look at one individual picture, each node will have a value here, 0, ranging between 0 and 255. Our Y, when we're looking at our output, so remember we have an input layer, we have some hidden layers, and then we've got an output layer. Our output layer corresponds to our labels here. So our labels are of our digit class. They range from 0 to 9. So we have 10 output layers. So we have Y sub 1, Y sub 2, which maybe I should have just called that. This is the probability of 0. This is the probability of 1. Oops. This is the probability of 2, all the way up to the probability of 9. So we have 9 output nodes, and we will have a probability associated with each of these. Okay. So this is the data set. What this looks like to the computer, to us, we see a 3. But we have to take an image and we have to convert it to a numerical representation in order to pass this to a neural network. Because you guys know at the end of the day, it's performing mathematical operations on it. It's applying our mathematical formulas. When we think about logistic regression, that's 1 over 1 plus e to the negative k. And that negative k is beta sub naught plus beta sub n times x sub 1 plus beta sub 2 times x sub 2, all the way up to beta sub n times x sub n. So we have to be able to convert something like an image to a numerical representation in order to apply those transformations to the image. So here, this number 3, what this looks like in our data set and what it looks like when we pass it to the computer is anywhere there's a white space, it's represented as 0. And then that's these ranging values from 0 to 255, representing how the level of grayscale here, the range between 0 being closer to white and 255 being closer to black. So here, these two values, for example, maybe these 2 pixels of the image are 255, but you can see leading up to that, it's 8, 38, 137, 146, 232, and 254. So this is how we break it down. And what we can do is we can actually put this into a array of values, a list of lists, or we can just add all of these together. It can be one long array, sort of like I had in that neural network image, and feed this to our neural network. Any questions so far before I jump to the next slide? Okay. This was surprising to me when I first learned this about how images are represented as data. Okay. So what we do here is we have 784 neurons of input. We take this pixel, this 28 by 28 pixel, and we break it down into each input piece. And so we have 784 nodes for input, and our output layer is a size of 10. We range from 0 to 9. And this hidden layer ends up being 64 units. And okay, so and then we can apply some softmax activation and transform that output into probability of yes or no if we want, but this is good for now. What does a neuron look like? So this is where we map. So there's a lot of neurons in here in this hidden layer, these 64 units. What's happening in here? When we take all 784 pixel values and we send it to this neuron, that's what's happening here. We're taking all 784 pixel values, all of these values that we had on this page previously, all those numbers, and we're sending it to this neuron. What is this neuron doing? How is it generating output that is being sent to these next neurons in the network? Here's what's happening. At the end of the day, this is all the math and formula that you guys have already learned and you're already very familiar with. So we have our x1, x2, and xn. I'm going to oversimplify this, and we're just going to say our image has 3 pixels, and 1 pixel is 0, and 1 pixel is 10, and the other pixel is 100. Okay. So we have this 3 pixel image, 0, 10, 100. Here, when we say weights in neurons and neural networks, you're going to hear a term called weights and biases. The weights are equivalent to the parameters that we've been talking about so far. So what's happening in this neural network here is we're basically doing a y equals mx plus b. So we're doing a 1, here we're doing a 1 over 1 plus e to the negative k. So our over e to the negative k. And remember that k is equal to, this is equal to our beta sub naught plus beta sub 1, x sub 1, beta sub 2, x sub 2, plus beta sub 3, x sub 3, okay? Let's map this to what's going on in this picture. So our w's, those are our betas. So we have k is now equal to, and this b here, the bias, that's our b. So b plus w1, and then here's our x's are here. That doesn't change. X's don't change. X sub 1 plus w2, x sub 2 plus w3, x sub 3. And then we're adding all that together, which is where this summation function is coming from. And then technically this activation function, so this is actually k. This is k. We're going to plug this in here. This activation function is now where we're doing 1 over 1 plus e to the negative k. We decided that we're going to do a sigmoid activation, and that's how we get our output. So the output is a probability that ranges between 0 and 1, because that's what we get from that activation function. So essentially the combination of the activation function and the summation function is logistic regression. So we're applying logistic regression here if we use the sigmoid as our activation function. So the reason I say if we use sigmoid as our activation function is another key word here in neurons, and there's different ways that you can transform this k. And it doesn't have to be 1 over 1 plus e to the negative k. There are different activation functions that can create probabilities that range between 0 and 1. And so we do not have to apply a sigmoid activation function, but if you apply a sigmoid activation function, this one neuron is the same representation as our neuron, as our logistic regression. However, but there's different terminology. Instead of calling the parameters, the betas here parameters, they're typically called weights. So these W's are called weights along these edges from these input neurons. And the B here, instead of being called our intercept, this is called our bias, and every neuron has a bias term. So let me just be hyper clear here, and let's map this k value. So in our case, k would equal, and we'd have some bias value here. Let's say our bias is 1. So k would be equal to 1 plus whatever we determined our weight was here, w1 times 0 plus w2 times 10 plus w3 times 100. So those are the weights that we're applying to these pixels on input, and then whatever the result of k is after evaluation, we plug that into the activation function. We plug that into the activation function, and that gets transformed into a probability. So output is a probability in these neural networks. The other piece I want to highlight here is that you probably won't see things written out. So they really like to simplify this and simplify the format. So what you're going to see, instead of saying k equals 1 plus w1 times 0 plus w2, w2 times x sub 2, w3 times x sub 3, you're going to see this notation as you're reading and as you're learning, as you're going through these resources. Instead of that, you're going to see w, x, And sometimes they'll have the plus b, other times they'll just say wx. So when we say wx, when it's a capital W and a capital X, they're writing that in linear algebra notation to imply that we're taking all of these w's times all of these x's in that order. So w1 times x1, w2 times x2. This is just a simpler way to write it, and they may or may not have the bias term in there, but the bias term is always there. So it's really w times x plus b is probably what you'll see, which is why this g of x is this function. It's a function. G of x takes w times x plus b. Okay, let me pause here for a second because that's a pretty big jump. Is this resonating with you guys? Pretty cool, huh? You guys understand neural networks more than 99% of people now, and what's happening in here. So everything that you've learned, linear regression, logistic regression, maps to this is what we were building to. So it's a fun little exercise that I would encourage you guys. Maybe I should make a notebook for this. A fun exercise to do is make a neural network with one neuron, just one neuron here, and train it on a training set and see what the output is and the performance and the classification, and then train a logistic regression. And what you're going to see is you're actually going to get the same results. So a one neuron, if we just have one neuron, what's happening in here is exactly what we said on this slide before. We're just doing y hat equals w x plus b, which is weights times our x input features plus our bias, weights and biases here. And that's the same as a logistic regression. The difference with a neural network, there's quite a few things we can do, but at the simplest level, the biggest difference is we just have a lot of these. And now we have, let's think about how this works. Now we have here, we're doing wx plus b. I'm going to call it b sub 1 because the bias is different for each of these neurons. They're not the same bias value because remember we train them. So wx plus b2, wx plus b3, and what's output from each of these is a probability. Maybe this is 0.8, maybe this is 0.2, and maybe this is 0.1. And then what's fed to this neuron here, it also does wx plus, in this case, b sub 4. And what it's doing is we have our y hat is equal to beta, our bias plus this. I'm going to call this w1. I'm going to call this w2 and w3. And this would be some weight. This is the output. These are the probabilities. So these are our x's in this case. So this would be y hat equals b plus w1 times 0.8 plus w2 times 0.2 plus w3 times 0.1. So now we have a logistic regression that takes as input the probabilities output from the other logistic regressions. So it's a chain. If our activation function is a sigmoid function, which like I said, not all of them are, there's a lot of different parameters you can change with a neural network. Just like we know with all of our machine learning methods, there's parameters we can change. In random forest, you can change the depth, you can change the min samples at leaf. There's a lot of things you can change about a neural network as well. One of them's activation function, but if our activation function is a sigmoid function here, then these nodes are sending probabilities into this neural network, uh, which are applied to weights, which are trained in the neural network, which we'll talk about how it does that. And then this then generates a probability output based on that. Pretty cool, huh? Any questions so far? Let me pause for a second. All right. I think that's super neat. So how great. We've got all these formulas. You've got these. So I one thing I want you guys to take away is what are weights and biases in a network. So weights here, one fun thing to do is like count how many weights and how many biases are in a network. Have you ever heard someone talk about a large language model and say how many parameters are in the network? They'll say, oh, this large language model has 2.5 billion parameters. Now you guys know what that means because the parameters are the sum of the weights and the biases. So the parameters in a neural network equals the sum of the weights. This is a weird way to say this, but the weights and no, I'm not going to do that. We're actually going to say this. The weights plus the biases, the number of them, the count of them. Okay, so let's count them. Let's assume, let's forget about this node here because it's not really in the picture here. This was trying to, so let's assume there's 4. This is x sub 4. So we can count the weights and the biases. Okay, so here we have a weight, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we have 15 weights. Let's count our biases. We have 1, 2, 3, don't forget this one, 4. So we have 15 weights plus 4 biases. Great, we have a 19 parameter neural network. So there's 19 parameters in our neural network. Now imagine 2.5 billion, it gets really big and very big and very large and very complex. Okay. How do these things learn? So that's right, this is the reason I was saying that. So we've got all these parameters that a neural network needs to change. At the end of the day, each of these W's represent a number, a fixed number. And the B's represent a fixed number. We know that from these formulas. We know that from linear regression. It's 10,000 times the number of bedrooms you have in your house, and that says every time you add a bedroom, it increases the price of the house by $10,000. How does it find those numerical values for these weights and biases? How do neural networks learn? So that's what we mean when we're saying we're teaching a neural network, we're training a neural network. We are finding the optimal values based on some optimization function. We're finding the optimal value for those weights and biases, for those parameters. We are training the parameters of the neural network. So we're setting what those numbers are in those logistic regression functions. And we do that ultimately through back propagation is a key term that we won't dive in here because it's kind of a little bit heavy on the math side. However, I would highly encourage that you guys watch a few videos on back propagation. I think it's great. I think it's really, really useful to know how the neural network calculates the error and propagates it backwards through the network. And also gradient descent and how it adjusts the weights using algorithms like gradient descent. So forward propagation is another key term here. This is the way the data moves through the network. So notice that the data didn't move backwards when we were talking about that. It only moves forward in this forward propagation framework. So each neuron calculates the weighted sum of inputs. The weighted sum of those inputs applies a activation function and produces output. So that's exactly what was happening here. Weighted sum of these inputs applies an activation function, which is sigmoid in this case, to create that 0.8, and then produces that output. The activation function is what's applied to those inputs, and in order to turn it into that probability for output. You guys are already familiar with the sigmoid activation function, which generates values between 0 and 1 and creates probabilities. That's that sigmoid activation function. There's a lot of other activation functions. ReLU is one to maybe be familiar with, and it outputs values between 0 and infinity. And it's
What does that
commonly
mean?
used in. That's a good question. I'm looking it up. Rectified linear unit. And it's going to look. So if this was our sigmoid activation function, the ReLU, let's see this, let's make this 0. The ReLU function is going to look like this. So it's a different way of creating a signal and a different way of sending a signal. You know, it's off and it's off and it's off until it's on, and then it turns on, and the signal turns on very quickly. So it's a different structure for, if you're thinking of like the brain and generating signals, it's a different structure for generating that signal. Okay, so at the end of the day, what if we have a neural network and we're trying to predict house price, and our y hat was 101, and our ground truth was actually 100. So y equals 100. We know that our error, we were off by 1. We know that we were off by 1. Switch colors here. And we can tell that to this node. We can say, hey, you were off by 1. But remember that this node was composed of input from here and here. So that node also has to tell the nodes behind it, you were also off by some amount. You know, you gave me this probability, which caused me to be off by 1. And if you had adjusted that and gave me a different probability, I would have had the right prediction here. So the first thing to do is the loss calculation. First, we need to calculate the error by comparing what we predicted, y hat, with the actual output of our function. So we have here, we have 1/2 y hat minus y squared. And then we can send this information backwards. We can basically compute the gradient of the loss with respect to each rule, with respect to each weight, using the chain rule. So there's a rule in calculus called the chain rule, and we can basically chain these calculations together to evaluate what the loss was. So that's sort of how we can send information backwards. We're not actually sending information backwards. We're applying some cool math to enable us to calculate that in a straightforward way. So we're applying some calculus basically in order to send that information backwards. Once we know where the change, once we pass back that loss, pass back that error, we need to update the weights. So if we just make predictions the same way, we're going to get the same error. So we need to change the weights. We need to change the parameters. And we can update the weights using gradient descent. And gradient descent we'll talk about here in a second, but it helps us figure out how much should we change the weights. Should we change the weights a lot? Should we change the weights a little bit? And when should we change them more aggressively, and when should we slow down in our changing adjustment of our weights? Oh, here's our gradient descent thing. So in gradient descent, we want to find the optimal value for some parameter that we're trying to change. We want to optimize our cost function. And let's say we have a parameter. We have a parameter and it equals 100. Well, how do we know if we should change it to 200 or if we should change it to 99? Should we make a big adjustment or a small adjustment? Basically, we can assess. Our goal is to get to this bottom point here. Our goal is to have no error. If we're at this bottom point here, our error is 0. We can use some math, we can use some calculus to calculate something called our gradient. So we can calculate this line here, which tells us how steeply are we descending down this slope. Imagine you're a ball. You want to get to the bottom of this uh, uh, I don't know, the bottom of you want to roll to the bottom of this hill or valley, I guess. And so the gradient can help us know which direction. So if we know our gradient, we know we don't want to go up, right? We know we want to go down. We don't want to go up. We don't want to go to 150. We can already tell that's not going to help us because we want to go down. We want to go to the down bottom of the hill. So that's what the gradient can help us do. We compute the loss with respect to each parameter, and the gradient is the vector of the partial derivatives that points in the direction of the steepest increase for the function. So we know we want to go down. The next question is how much? Do we go down to 90, or do we go down to 10? How dramatic do we want to be? And as we're going down this gradient, if it's a really steep gradient here, maybe we take bigger steps. So in the algorithm, we can decide our step size. And maybe as our gradient, our slope here, this slope of the gradient of this slope gets closer and closer to leveling off. As we get closer and closer to leveling off, we take smaller steps. So maybe we do change it by smaller amounts. So in this case, maybe we make a big change and we change it to 10 because we're at the top of this slope here. So we can adjust the parameters in the opposite direction of the gradient because we want to minimize the loss. And we can leverage the learning rate, how big our steps are going to be, to control how much we change the parameter. And this happens for every parameter inside of our neural network. So there's a fairly substantial amount of math going on here. Okay, that's as deep as I think we're gonna get there. So a couple of things to note: that the goal of gradient descent is to find the global minimum, which means the lowest point. So this is the global minimum here. But just recognize that there's quite a few local minimums, which are not the optimally low point, but they're low. And we can get stuck in these. So if this graph represents the combination of all these parameters that we could try, and then the outcome with respect to the loss. So we want to get to the bottom because we want the loss to be 0. There are quite a few things that can make this challenging, and there are times when we will get stuck. I think I actually have a slide for that. Yeah, here we are. So There are some challenges. There's probably more than this, but here are a few challenges. Oh, and we're at 9:05. Let me see. Okay, let me see. We have quite a few more slides here. Up to you guys. Do you guys want to go a few more minutes, or how are you guys feeling?
I have no preference either way, but I do feel like we're missing a lot of classmates. So
True. That's a good point. Let's talk about these challenges. Uh, and okay, I think let's talk about these challenges and then we'll come back on activation functions because I think activation functions, we've already talked about them quite a bit, and it's like a perfect place to pick up and refresh and come back and um, start from here. So let's talk about a few challenges with gradients and finding the optimal parameters for neural networks. One is local minima, which I talked about. I don't think it's one of these pictures here. I guess it's this one. So local minima is when there's clearly a global minima, which is way better if our loss is down here. But we get stuck here using our algorithm where we said we're going to take big steps and then smaller steps and smaller steps. And and this is where we get stuck. Then there's also saddle points where it seems like the gradient is zero, and so keep taking infinitesimally small steps, like this picture here, or the algorithm stalls out. But really, if we applied other approaches or powered through that, then we would have found this minima here. And by the way, these pictures, these minimas, these are like theoretical. Like in reality, we don't know what these actually look like. These are things that can happen based on training data that we've seen. But in reality, when you are trying to find the lowest point, when you're trying to find the optimal parameters, we don't know that if we keep pushing, we're going to, of course, hit this point here. So these are to be discovered. There's also vanishing and exploding gradients, which can become extremely small or extremely large and lead to a lot of difficulties in training. And then there's these kind of like loop situations that can happen. So with this one here, what's happening is we're starting up here and then we're saying, oh, we need to decrease our parameter. And so we decrease it here and we move in this direction with our parameter that we're tuning. And then we take too big of a step size and we jump all the way over here. And then we say, oh no, we need to go the other direction with our, now we need to go and increase our parameter. And so we increase it and we step here and we're like, okay, we need to increase it even more, but we do too much and we go over here. And then you get stuck in this like cycle here where you just keep bouncing around. The other one that can happen is jumping over. We can accidentally so this in this case your step size is too big. We should have taken smaller step sizes, so this is too big in this case. Or I guess maybe it'd be too small if you wanted to jump over here. But this one, in this case, we also are taking too big a step sizes. So we took a big step size, jumped from here to here, and we took another one and we jumped from here to here, and then from here to here, and here to here, and here to here. And we ended up hitting that global minimum in this picture. However, this minimum could have been way down, here, and we could have missed it. So there's pockets that we could miss when we're training these parameters. Okay, when we come back, we're going to talk about activation functions and why they matter, how we take how these activation functions allow neural networks to learn in a nonlinear way, and how they can enable them to learn complex patterns. There's a several different activation functions. The sigmoid is one that you're already familiar with for binary classification. I think you guys will really appreciate also the softmax function, which is used for multi-class classification. And it's really just a generalization uh, on the sigmoid function, which is pretty cool. So softmax and sigmoid are very similar. Sigmoid's for binary, softmax is for multi-class. And then we have the TANH and ReLU, which are also activation functions here, pictured below. So we will come back and talk about these and how they're used in the neural network. So hopefully this was kind of a fun section for you guys. Let me end the stream here.